The 300-degree error. The James Webb Space Telescope just captured a direct image of a gas giant 12 light-years away that is 300 degrees colder than our best atmospheric models predicted. This target, Epsilon Indiab, is not just another exoplanet discovery. It is a failure of our current predictive physics. While the marketing teams focus on the image itself, the engineering reality is that our data and our simulations have just diverged at a fundamental level. This discrepancy exists because of one specific mechanism: the presence of thick water ice clouds that we thought were impossible to detect at this distance. Bypassing the transit bottleneck, 95% of exoplanets are found using the transit method, which relies on the geometric luck of a planet crossing its star. Epsilon Indi A flat was found using the MIRI coronagraph, a hardware-level mask that physically blocks stellar light to reveal the planet's own thermal emission. By observing at mid-infrared wavelengths, Webb can see objects that are too cold to emit visible light. This is the first time we have directly imaged a mature, cold planet similar to our own Jupiter. It moves us away from studying glowing, newborn planets and toward the stable, cold systems that actually dominate the galaxy. The data suggests this planet is roughly 6 times the mass of Jupiter, but its chemical signature is missing a vital component: the model failure. Before these 2026 observations, every chemical model for a planet of this mass and temperature predicted a clear atmosphere dominated by methane. The actual MIRI data shows a massive deficit in infrared flux where methane should be transparent. Think of it like looking for a flashlight in a dark room, but finding a thick fog instead. The only physical explanation for this data is a high-altitude layer of water ice clouds. Our models failed because they oversimplified the cloud condensation physics for cold gas giants. We assumed these atmospheres were static, but the Webb data reveals a dynamic, cloudy environment that actively masks the chemical markers we use to identify planets. The Jupiter Proxy, Epsilon Indi A flat, is essentially a test case for our own solar system. Because it is older and colder than typical targets, it serves as a proxy for Jupiter. If we cannot accurately model the cloud decks of a massive gas giant 12 light-years away, our chances of accurately identifying life-signifying gases on an Earth-sized planet are negligible. The cloud noise we are seeing here is the single greatest technical hurdle for future missions, like the Habitable Worlds Observatory. We have reached the limits of simple atmospheric theory and hit the wall of real-world meteorology. The signal under the noise. The discovery of clouds on Epsilon Indi A flat proves that our current spectroscopic tools are blind to the most common types of planetary atmospheres in the local neighborhood. By analyzing the failure of the methane models and the success of the MIRI coronagraph, we see that the difficulty of finding a second Earth is not just about telescope size, but about the atmospheric noise that masks biosignatures. For engineers and mission strategists, this is a pivot point. We must now move from simply detecting planets to solving the problem of cloud opacity in cold atmospheres. What was previously categorized as a clean chemical signal is actually a complex meteorological puzzle. This finding forces a total rewrite of the retrieval algorithms used for exoplanet atmospheres. Without this correction, we would likely miss the chemical markers of a habitable world even if we were looking directly at it. Watch for the updated PTRAD transcode release in late 2026, which will be the first attempt to integrate these cloud physics corrections into our search for life. Subscribe for more.